like I said, the PC relative addressing and pseudo addressing, I want you to actually go through the process here of taking a 16-bit value, sending it 32 bits. So let's just say it's, where the last 3 are. So basically you're just concatenating zeros and outputting another array, which you'll have experience with from your, the carry select adder, where you took 2 16-bit values out, put them together in one 32-bit array, and then put the value on the output. In this case, that's just taking a 16-bit array, putting a bunch of zeros in the front. Now it's 32. Then you have your shift left logical, which you've already done. Hey, McKenna, if you want to turn your assignment. And then just taking you can pick values. You need to have program counter, so some sort of number you put in there. Hard code the number 4 in, because as you can see, you're going to have this in a couple of places in the data path. And then have this value output into yet another adder. And then that value, don't worry about coding up. Actually, you know what? Since in this section you're going to be coding up instruction memory, you can use it as a test case to just put all that stuff together. Because in problem 3 and 4, which we'll go over in a second, you actually are doing the instruction memory and the data memory to here if you want to turn the assignment. Just put it right here. And then for pseudo-direct, you're taking a 26-bit value, using your shift left 2, which you've already done, and you have a 28 value. Then take the same PC plus 4 that you did previously, and then what you want to do is, does anybody remember from last class what this value is? Concatenation, right? So what am I asking you to do here?
Add 4 bits to the end of the 28 bits you have.
Okay, so there's part of what you said is correct and part of what you said is not. What I want is, if we go to the MIP screen sheet, and you see on here, let's go to File Explorer. I'm sure I have the MIP screen sheet in here. Sort by name. Where's the MIP screen sheet? No MIP screen sheet. Okay, but if you look at the MIP screen sheet, you'll see that you have the 4 most significant bits are concatenated. So not to the end, to the front. That's the part you got wrong, but everything else you got right. So you're going to have a 28-bit value, and then you're going to have the 31 through 28, right? So if you're taking it from, if you remember, this will, in your array structure, it'll be 0 through 3, right, because they go backwards. And then you're just going to put those 3 at the front and then send it back to instruction memory. Right? And so those are 6.1 and 6.2, 6.3 and 6.4. The way you're doing is you're taking these, here's the test cases to make sure you know it works. So here you're going to have a set of instructions that use byte addressing. So the input that you're reading, remember for the previous section, you're reading in 32-bit values from your registers. Here you're going to be reading in 8-bit values. So you're going to get some sort of input, some sort of 32-bit input. And for instruction memory, it's going to be from your program counter. And from data memory, it's going to be from your ALU. Right? So you need to have some sort of way in which, so you have 32 bits, and you need to have some sort of way in which you can glean that value to get your array value. And so the arrays go to integers, right? And you have some sort of 32-bit value. So you might want to code up some sort of way to convert a 32-bit value to an integer. How would you go about doing that? We've actually done math problems in section 3. If I have an 8-bit value, right? Let's say I give you this value. That's 5, 7, 8, right? How would I calculate this value?
You just cycle through all of the digits and add 2 to the whatever power, and keep adding. And so forth.
So you have some sort of incrementer, right? So 2 to the 1 is 2. 2 to the 3 is 8. So now we have 10. And so what's 2 to the 5 is 32. So that is now 42. The answer to the life, the universe, and everything, right? So, very good point. What was the question? We didn't ask the question. So I would do, so just have a little thing in there that does that, brings in your 32-bit value, and gets your element in your array. Now, the next part is you need to be able to read and write to everything. So you want to read in for the instruction memory, you want to have the function where you're writing to it. So basically, you're taking those 8-bit values and going through and filling out your arrays. If you look over up here, so for struct byte mem, this is what I call it. Basically, I have an SRAM cell of bytes. And so for registers, I had as bits. So bits was 32, and I defined byte as 8. So if you go through that, so I had a function in there, initialize registers, and we went through in a tremendous amount of detail how to do that. So for these problems, you want to do something similar, except you want to have 8, byte arrays for instruction memory and data memory. Now the key thing is you want to be able to pull it out. So what's going to happen is you're going to have some, get value where you're getting some 32-bit value. Then you convert it to an integer by doing what we just told you to do. Get that value and then the next 3. So that value we calculated for the 32 bits. Let's say that this is our instruction. So basically, I'm going over the same thing I just went over with Brian a little moment ago, right? So this is my instruction. We have calculated this is an instruction. The number that you have calculated is going to be this one here. So you have to get, but I need a 32-bit value out, right? So you need to get that one, then plus 1, plus 2, and plus 3. And so what you can then do is you can have 4 loops. You can have a loop that says for I equals 0, and you just go most significant bit all the way through. And then these 4 values, you're going to combine them, and that is your instruction. And so I've defined the number of values. I'll actually post. I'll post test cases you can do for instruction memory and data memory that will have the exact sizes, because I have the instructions set at 4,092 bytes and the data memory set at 512. So that's why. I don't have the. But yeah. So basically, I'll send out that information. So this is the end of the section 6 coding assignments. Your project 2 is going to be sections we do 2, 3, so it's going to be 4 through 6. And then for those groups that you're going to want to go back and correct what you got wrong in sections 2 and 3, because as you can see, everything's starting to build on each other. So by and large, the project submissions were very good. You probably saw that I posted your grades. The median was a 48.5, so half the class got a 96 or 97 or better. But there were some struggles. I think the big thing I hit people on was not commenting. 2, make sure the code you submit actually compiles. Even if you have to comment out stuff, you're allowed to put it in your your challenges section. We tried commenting this and it was tough, and here's what we tried to do. And I was very happy with. Usually about 6 hours out, I can check the submission window and no group is submitted. 5 of your groups submitted before 6 hours before the project was due, and so I'm very happy with that. That means you guys are working ahead and keeping up. That shows that you're going to have you're going to be good engineers, because if you're kind of doing that level of work ahead of time, that means you're people who can get work done, and then you don't have to rush and worry about everything at the last minute. Project reports, by and large, were excellent. In fact, I think there's one group I want to use as the example in the future, kind of for, because I'll have CMOS, and I'll say, well, here's look from 385, and they did a really well done diagram of the ALU. And one thing, I didn't hammer you guys on it this time, but next time I will be a little more so. you can't just use figures from the internet and claim they're your own. So that's plagiarism. While it's ultimately harmless because you're not claiming it's your own work, you're not claiming you invented matter. Ultimately, at the same time, when you get into industry, what you have to do is you have to indicate where you got everything. Otherwise, if you have these Samsung Galaxies and you have to do that little slide out instead of just pressing the button to answer the phone because they didn't document everything properly, and Apple sued them because they had a similar phone pickup sprite. So that's what happens when you don't document properly. You get your company sued. So just a good habit. I'm not saying you guys are malicious or anything, but just a good habit. So that is due. I have it. I'll tell you why I have the dates that I picked the way I do. So if you've looked at the syllabus, you probably noticed that on the 25th, that Sunday is when I have the project due, and then I have the test the following Thursday. The reason I did it that way is because if I put the test the previous Thursday, what's everyone going to do? Everyone's going to study for the test exclusively, and then I'll put you in a position where you're forced to put the coding off. Whereas if you're doing the coding is going to help you study for the test, and then you'll have 4 extra days to be able to prepare for the exam. So that is why I've set it up that way. So those are, so we've got through section 6. I believe the end of section 6 is where we're also going to cut off the exam 2 study material, because section 7 we start getting into the data path and pipelining and all that. So that's just kind of a preview of what we'll be doing here on out. So does anybody have any other questions before I get on to cache hierarchy and all this and how everything works? All right, so we ended with this principle of locality. I probably mentioned this last class, but definitely understand what the principle of locality is, and definitely be able to tell me the difference between temporal locality and spatial locality. And then memory hierarchy, this is what we're going to cover today. So we're using multiple levels of memory to improve memory access time. So here's what this means. So here's a little diagram where you have your processor and you have these registers, right? The registers are really fast. We have 32 of them. We only have 32 of them in depth. And then we have this data memory. We have 512 bytes that you're going to use. We can do in the actual data path, it'd be 512 megabytes, but I don't want to consume up too much memory on your computer when you're coding. And then what we're going to be doing is that the next level is going to be higher than that, and the next level is going to have more memory elements than that. But here's the challenge. If you're making memory fast, one of the issues is cost. So this is the whole point of this was to split up the difference between fast memory and inexpensive memory. Do you remember what does RAID stand for? Does anybody know what RAID stands for?
RAID,
RAID, R-A-I-D. Redundant arrays of inexpensive disks. It hasn't been a TGO yet, but actually the guy who invented RAID was David Patterson. So same guy did your textbook, right? So basically the whole point is you have these redundant arrays of inexpensive disks, which you're able to store memory in a non-volatile manner. So you have this fast volatile memory that costs, and you have the cost is going down while speed is going up, right? So as a result, you're trying to have each element of the memory hierarchy is a subset of the next level. So if you have level 1 here, you're going to swap this out, but this memory is also going to be contained here, and all of this will be contained here. So we're going to be getting this memory swapping. And so does anybody remember the term I threw out when I talked about if you have more memory swapping than performance going on? What's that term in operating systems? Thrashing. That's exactly right. Who said it? Good job. Whoever said it. That thrashing, that's the idea where you're just switching out memory so much. And that's what happens when if you leave your computer running too long, you have all this thrashing. And the reason why there's thrashing in the case of Windows, or especially the older version of Windows, is they didn't do a very good job of deallocating pointers. So they were holding on to memory elements, and of course they had to go to other places, and they could only run a couple of instructions and had to switch back because everything else was saved. They had a lot of thrashing, and that's why if you leave your computer on for a long time, the performance slows down. So malloc and calloc, important. So these levels that we're going to learn about is this idea called cache memory. So we're using it to take advantage of processor and main memory and temporal and spatial locality. So the whole idea is we need to know when we want to swap items out. And the operating system has specific algorithms that it can use to try to optimize as best as possible which blocks to put in, which blocks to take out, and have that in there. So we define cache memory here as the level of memory hierarchy between the processor and main memory where RAID is and all that. And it's used to take advantage of temporal and spatial locality. And in 6.7, I define a block as the minimum amount of data transferred between cache and main memory. So we have some sort of block here. And then when the data is transferred, I want to go level 3 to level 2 to level 1, and level 1 back to the processor where that goes into the data memory. And then if you want to go into the registers, you perform load word and store word. And so the minimum size block is dependent if you have certain calculations for how big portions of your program are going to be. So you can swap those back and forth to different levels of cache to eventually interact with the processor. So here you can have 512 bytes, right? So define that. So we've defined our block size in the data path as 512 because that's what data memory is going to be. And then the data is transferred based on that. So the TGO is only a definition. You don't need to include the drawing. Right, so does anybody have any questions about cache memory or blocks? I'll show some examples here a bit. So now we're going to talk about this idea of cache hits and cache misses. So when you have, let's say you got data memory, right? And you have an instruction, and the instruction says, if you probably figured out the number that you can calculate from the ALU, 2 to the 32 plus 2 to the 32 minus 1, is greater than the amount of memory you're going to actually have in data memory, right? So what you can have is if you calculate a bigger address than what's currently there, what's going to happen is the operating system will get the block that you want, swap it in, and then you can calculate it out. So if it's there, we go to data memory, the item we want is there, we call that a cache hit. And that means if the requested data is in the cache, read or write operation is performed directly in the cache, and you don't need to do anything. So it's just the amount of time it requires to get the item from the data memory and load it into the register. Now the hit rate is the probability, it's defined as probability that you're going to get a hit. And then you can calculate a lot of stuff in operating systems is calculating hit rates and calculating miss rates. So I indicate the values between 0 and 1 in the case of those, for those of you who haven't had any probability-related statistics course. All probabilities are, it's like 0 to 100%, but then it's like a fraction, right? So 0.87 means you have a 87% chance of finding the item in cache that you want to find. And a cache miss, and this is where swapping becomes important. If the requested word, I use word because in MIPS 32 bits, if the requested word is not in cache, a block of words containing the requested word is brought into the cache, and the processor request is completed. So here's what that means. I want a load word instruction. Give me this block. And then I find out that it's not there. Well, now I need to check the next level. Are you there? First block word I'm looking for. No. Now I got to go to the third level. Am I there? No. And then if I'm not there, then I got to go to the data memory. Not the data memory, non-volatile memory. Now the challenge with that is we're going to go over in a little bit, is that going into this slower memory can oftentimes take 100 times longer than going in this cache. So we're trying to optimize speed. Now virtual memory is where you're using levels of actual non-volatile memory as cache. So Java is kind of using this these non-volatile memories as cache to be able to make bigger blocks. Now, there's pros and cons to that. If you notice you've ever run a virtual machine, it runs a lot slower. That's why. So the requested word is not there. We bring the requested word into the cache, and the processor request is completed. And then the miss rate is the probability that we have a cache miss. And that's just 1 minus the hit rate. So if you have an 87% chance of getting a cache hit, that's 0.87. 1 minus 0.87 is 0.13. So therefore, you have a 13% chance of having a miss. And we find that as the probability the requested memory item is not in the memory is equal to 1 minus the hit rate. And so we have all these different probabilities. So each cache hit percentage is going to be different in different levels. So if you're using spatial locality, that means that you're grouping everything together. So you're going to have a high probability in level 1, which is the level that interacts with the processor. Level 2 is going to have a slightly lower probability, and then level 3 is going to have a slightly lower probability than that. So the way it works is, if I have a 90% chance of hitting level 1, that means I have a 10% chance of having to go to level 2 and level 3. So 10% times, okay, so let's say level 2 is an 84% chance. So I've gone 10% of the time I have to go to level 2, and then 84% of that 10%, I'll find it. But then that means 16% of the time of that 10%, I have to go to level 3. And then there's going to be some sort of other calculation, which we'll go over. And so by knowing all those probabilities, we can calculate the average amount of time it will take to actually access a memory element. And that's known as average memory access time. And I will abbreviate often as AMAT. So for level 1, probably everybody's getting everything but miss rate at this point. So for 6.9, TC is your cache access time. So if we have one level of cache, this is the equation. So I'm going to start building up an equation for 3 levels of cache. So we're going to do this, and we're going to do a corresponding problem for these next 3. So the TC is the cache access time, TM is the main memory access time, and H is the hit ratio. So this equation, what this means is your hit ratio is your hit rate. So if you have 0.9, so that's 90%, times the amount of time it takes to actually access an item in the cache. And then what's going to happen is plus 1 minus hit rate, so that's going to be 0.1. So here's how this works. First, you have to go to the cache. Is my item there? It is not there. So then I have to go to main memory. Right? So the example question we're going to show here in a second is a good example of what's going on here. So example 1, given a level 1 cache, that means we have one level of cache memory with a hit rate of 95%, a cache access time of 5 nanoseconds, meaning it takes us 5 nanoseconds to get just an item from the cache, and a memory access time of 100 nanoseconds, find the average memory access time. So here's what we're going to do. We're going to use that equation, and so our hit rate is 95%. That means 0.95 times 5 nanoseconds. So that's 95% of the time, that's what we're going to need. Right? So then 5% of the time, here's what's going to happen. So that's 1 minus 0.95 or 0.05. And then I'm initially going to check my cache, and I'm going to go, is it there? No. Then I need to do the next 100 seconds. to get everything from main memory. And so this number comes out to 10 nanoseconds. So does that make sense how we did this? And so next, example 6.2, I'm going to scroll up past the definition of average memory access time and have example 1 and example 2 both on the screen. Given a level 1 cache, and I've stated everything else, determine the speed up of a processor without cache. So here's what that means, the same processor without cache. So I have this original equation in the denominator, right? So this is a performance problem. So all the way back to section 1. So here I have that same equation. And then if I don't have cache, well, then it's just 0 times 5 nanoseconds. And then it's going to be 100%. But I never access the cache, so it's just 100 nanoseconds. So then this just becomes 100 nanoseconds divided by 10 nanoseconds. So by adding that one level of cache, we have achieved a speed up of 10. So that's why cache memory is important. Now, the one issue with cache is it requires actual cache, which is why we deal with different levels of memory. Yeah, it is very funny, but it actually is very true. So the different levels of cache are going to be a little slower, but they're going to cost less. So as engineers, the reason why understanding this concept is important, other than knowing what's going on in your advanced digital system, is that good design requires good compromise. This is a really good example of how compromise in design allowed you to keep costs down for your customer, but ultimately be able to achieve high performance. So in TGO 6.7, it's 6.10. Okay, so all the numbers are going to be off. So this should be 6.10. All right. I've added things. All right, so 6.11. Basically, we're going to take this, and now we're going to start doing these probability branching here, right? So it's H1 times level 1 access time plus 1 minus that first hit rate. So we're going back to that same problem. As you can kind of see, I'm actually building up here. So if we had 95% here, this is 0.95. So then 5% of the time, we need to start worrying about the second level of cache. So then we're going to have some sort of hit rate for the second level. And then what's going to happen is, at that second level, we're first going to access cache 1. It's not there, so we then go to cache 2. Right? And that happens some sort of percentage of the time. So this problem we're doing down here, I've notated as 85%. So then 15% of the time we don't get cache 2, we're going to go, it's an instance where we go cache 1 plus cache 2. I check it there, it's not there. And then I go into the memory, the main memory. So and really, because of the way we're doing this cache, what ultimately happens is we're only going in this case, 15% of 5% of the time. And you see in the problem, and then I've done this in the level 3 cache to give you more of an example here. So that should be 6.11. Yeah, it should be 6.11. So they're all off by 3. Sorry. Actually, what I could do, that's section 7 lecture notes. Let's not scare you guys yet. Section 6 lecture notes. We'll just use this while the PDF is off. So same thing here, hit rate 1 times access time 1, 1 minus hit rate 2, and then we go into another so I've separated by bracket, so you can see the bracket here, and then I've made this bracket red, so you can see the difference that I have here, right? And so we have the same thing. We have hit rate 2 times cache 1 plus cache 2, and then when you have that second missed hit, then you have the hit rate of the level 3 cache. And then if you're able to successfully get it in level 3 cache, it's just the time for cache 1 plus time for cache 2 plus time for cache 3. But if it's not there, then we have the opposite probability. And then we have 1 minus hit 3 times cache 1 plus cache 2 plus cache 3 plus the main memory. So these next two example problems will show why adding the level of cache helps out. And you'll actually be able to see why we stop at 3 levels of cache typically. So in example 6.3, we start out with the same thing from example 6.1. So we give it a level 2 cache with a hit rate of 85% and a cache access time of 7 nanoseconds. So we had level 1 with 5 nanoseconds and we had main memory with 100. So we use our equation. And so even if you don't remember, and the reason why I have you build this up is because you've probably seen a pattern, right? One common thing I saw from students in the past when I was a teaching assistant before I taught this course was students really struggled with building up level 1, level 2, and level 3. So those TGOs are specifically there to make you see how to build up the average memory access time equation in that way. So then we have example 3, and example 4 is going to add level 3. So hopefully you'll be in grade. So we have our equation. So 95% of the time, it only takes us 5 nanoseconds for level 1. So then we have the 0.95 here, right? So this means 5%, and you can see everything else is here in these brackets. So 5% of the time we need to either access level 2 or go to the main memory. So we now, 85% of the time we are successful in finding an item in level 2 cache. And that takes us 7 nanoseconds plus 5 nanoseconds, which gives us 12. So when you're going back through, this is 7 plus 5, right? So that's where we get that number. And then here, 1 minus 0.85, so it becomes 15% of 5%. We're going to require 5 nanoseconds plus 7 nanoseconds in level 2 plus 100 nanoseconds in main memory. So that's where we get 112 nanoseconds. And so when you calculate it all out, and by the way, I should probably indicate that when we get to level 3, you're going to see this on an exam. That is sufficient for full credit. Again, I'm not testing you on your ability to put numbers into a calculator. But here, what you'll notice is we're now down to 6.1 nanoseconds. So we were originally at 100, and then with 1 level of cache, we got it down to 10. And then in the second level, we were able to get it down to 6.1. So in 6.4, we're going to do processor in example 3. So you're going to the exam question will have you have 3 level cache. Cache 1's hit rate is 95%. Cache 2, and then with an access time of 5 nanoseconds. Level 2 has a hit rate of 85% with an access time of 7 nanoseconds. Level 3 has a hit rate of 80% with an access time of 10 nanoseconds. So you can see the access time is going down and your hit rate is going down just because of that spatial locality. Those levels are bigger, so that hit rate is going to be smaller just because you're trying to access a specific item. Then find your average memory access time. So we use that same equation from the TGO, And so the way it breaks down is 0.95 times 5 nanoseconds. So 5% of that time we're going to go here. And then just like before, 0.85 times 12 nanoseconds. Plus, now we go into level 2 miss. So that's 15% of 5%, right? And then in level 3, 80% of the time we get a hit. So we get 22 nanoseconds because we have 5 plus 7 from level 2 plus 10 from level 3. So that gives us 22. Right? And then 20% of that time, we have 122, which is 5 plus 7 plus 10 plus 100. And then when you get down here, it's 5.75. So what you'll see is if we had some sort of relationship between levels of cache and so if we had level 1 takes 100 nanoseconds, level 2 takes 10, then you have 6.1, and then 5.75. You can see how it kind of starts sloping off, right? So what happened is, again, we're dealing with money versus cash. And so you start seeing every time I add another level of cache, even though that cache level by itself costs less, by adding that fourth level, you're adding more cost. So you get to a point where the trade-off between cost and performance was too expensive. And typically, you're going to see right there at level 3, it was the sweet spot.
Does that graph, what's the limit as your money goes to infinity?
If you have infinite money, you can build an infinite computer, then you can do whatever you want. So there is no limit if you're Elon Musk, but if you're us, then there's a problem. So, yes, Brian.
I think he's asking, it seems like the time is converging to a finite value.
Right, so, I mean, it ultimately depends on the cache. There's no exact answer because there's the performance of each cache level is dependent on the design and ultimately your performance. But I was just showing this specific problem where it's going off. So there's no exact limit because I could make level 4 whatever I want, level 5 whatever I want. So, but eventually you're going to see that probably get to, actually, you know what? I think I figured out a better answer to your question. So level 1, what was our level 1 cache? What was the fastest speed of level 1 cache? Go back to 6.1. 5 nanoseconds, right? So that means that if we did everything in level 1 cache, then it would be 5 nanoseconds. So that's your limit. But we have to access data memory because we don't have a perfect computer. So your limit's 5 nanoseconds. So does anybody have any other questions about this? All right, so let me make sure I have. So this was. Oh no. Okay. Now that TGO numbers are right again. Okay. So as we get closer and closer to 5, the trade-off between performance and cost is not tenable. So here I have 3 different ways of controlling the miss rate of a cache. So increasing the cache size. So more blocks can be kept in the cache, so your chance of cache is reduced. So if you just have more blocks in each level, you'd think that even if money wasn't necessarily an issue. But ultimately, you kind of have to go down to, you ultimately have to go down to the different levels. You have to calculate each one. You have to test if it's there. So if you have a larger block, it actually slows your cache access. Larger number of blocks, it slows your cache access time. So the second part is increase block size. So you have the same initial cache size, but instead of having a block of, say, 512, we make it 124 240, 248 or whatever. However, fewer blocks in CAC actually increases the chance of a miss. So you're actually kind of having a little trade-off here between temporal and spatial locality. So you have more data available per swap, which increases the probability that you'll find what you want in that block. However, because of the fact that you have fewer blocks, you have to actually perform more swapping, which would increase your miss rates otherwise. So there's trade-offs between all of these different approaches. So there's no one correct way. And we're going to see differences between direct and set associativity later in this section as an example of that. And then ultimately, the one that seems intuitive is your increased hit rate. Just how do I reduce the miss rate, increase the hit rate? But your hit rate increases with your cache size. So either you're adding more blocks, or you're making the blocks bigger and you're adding more blocks to that, or however it works. But ultimately, hit rate depends on the block size. So this one right here, 6.12, that's a interesting description of engineering challenges, that you get to certain points where you've come up with some certain optimizations, but as you keep trying to optimize it, you're going to run into some other problems. Money coming into how does the block size do all this? All these things you have to consider as an engineer. So, and then this, I'll leave the last two parts here, but you can start seeing these drawings describe what I was talking about. So if you add more blocks here, and you add a cache, and but you have to ultimately, if you're trying to scan the cache, trying to find the specific items you want. Now, ultimately, when you're trying to take advantage of spatial locality, your operating system would want these closer here and here. So that's spatial locality. And so temporal locality just means the same items used over and over again. So the operating system here is not doing a great job of running the program. So if I try to put everything in one larger block, in this case it works because it's 4 pieces. But let's say I add one more piece here, right? And then I have to add my piece here. Well, hopefully that's at the end of the program. But let's say it's not. Let's say I do first 2, then I got to do this one. So then I got to perform a swap, bring this whole block in here, and then take care of this. Once I'm done, then I got to swap it out and bring this last one back in here to do these 2. So the chances of getting your whole program in there are better, but if it's not all in there, then you have real problems. So that's okay. So I've included this again. It's kind of described a lot of my the other things I mentioned earlier, increasing the block size to match locality. But as you can, actually, this is a perfect example of some of the problems. So here you have a block, you have all your elements that you're using, and sometimes they're hanging out here. So then increasing the block size requires more time, but if you have smaller blocks, then you can put them in back and forth in memory faster. So, okay, so how do we actually find these elements in memory? So we're going to talk about these concepts of everything's going to have an index, a tag, and a valid bit. And what we're going to be using this index, the tag, and these valid bits to be able to find precisely where an element is. And the reason why we need this information is because the way we're going to be swapping elements back and forth is by basically the tag is going to be, okay, so let me just describe each one, and I'm getting ahead of myself here. So the index is the numerical value used to indicate the exact location in the cache. So that's just simple. If I have a cache and I have 32 blocks, then I have a 5-bit value. So 01010. This indicates it's in block 8. So the tag is how we're actually going to be swapping elements back and forth, so we know where to put it into the cache when we get done. So a field in the table that contains the address of the information required to identify where the associated block corresponds to the requested data. That's a lot of gibberish at the moment, but here's what this means. So if you have a memory element, so we had the first one, so it's 0, 1, 0, 1, 0, right? So this would be your index. Now, if you're going to have more than 32 blocks to accomplish your memory, let's say we need 128, right? So if we have 32, then we can count for 64, then 128, right? So this accounts for 100. We can get 128 blocks in that level of cache. So this means that I can have 0, 0, 0, 1, 1, 0, and 1, 1, meaning that I have 4 different blocks in the next level of memory containing 32 blocks in the previous level. So if I need 32 blocks of the previous level there, then I'll swap out. I have 4 of those available to me. So this is your int tag. So the index is, I'd say going back to our road analogy, right? So each road can have potentially 32. So I start with this road. That's 0, 0. But then I need something over from this road. So I would just go to the memory, swap out, and say, instead of going to this one, put this one in the level 1 cache, and then I go in there to get it. So we use the tag and index to be able to relate those. And then the valid bit indicates whether or not you've actually, whether something in that hierarchy actually contains valid data or not. So let me scroll up a little bit for those of you in the back. And so we're going to study 2 types of cache mapping in this course. We're going to study, the first one is called direct map cache, and the second one's going to be set associative cache. So what I described to you here is what I just described to you using the tag and index is what's known as direct mapped cache, where you swap in a block and it allows you to actually use those last values in there to find it directly. So we define it formally in 6.16 as a cache structure in which each cache location is mapped to exactly one location in the main memory. And sets are going to have 2 or more. So that's set associative. And I'll show you 2-way set associativity in the problem. So the big problem that we're getting to at the end of the section is, here's your direct map. Show me how, I'm giving you a set of accesses. Give me the direct map, how fast it goes. Give me set associative. Show me how fast that goes. Now, here's how you calculate the size of the tag. So here, the size of memory divided by the size of block log 2. Right? So in that example that I gave you, right? So I had 128 over 32. If you're doing log 2, this just becomes the same thing as 7 minus 5, which is going to be 2, right? So that's why the tag, the field in which the table contains the address, the information, was 2 bits. And then your index is just going to be log 2 of the block. So a block was 32, so it's log of 32, which is 5. So what that means is whenever I swap a block in a direct map, it's going to use those 5 least significant bits to perform those operations. So if I have 512 bytes in my data memory, as you will have in your code, what would be happening if I were to have you code this cache hierarchy would be, if you had other elements, you would be swapping in 512 bytes. That would be the size of your block. So if I had that kind of thing, you had 512. I'm sorry, so 512 would be the size of your block. So that's 9. So if we have some sort of index to find it, what that means is you only need the 9 least significant bits of the calculated value to get the value in the memory, right? So if we are going back to our problem that we had earlier about trying to convert the integer to the binary value to an integer to find the array element. By using cache memory, you only need to check the 9 least significant bits. You wouldn't need to go all the way through all 32. Does that make sense? So that, Brian, getting that question you asked before class, so that's where the byte addressing really comes into play. You don't have to check those 9 least significant bits, and then you're good. Okay, so this next example is really going to show in detail what this direct mapped caching means. So here, what this is we have, so we can say this is level 1, we can say this is level 2, right? So here, the block is 8. So we could have 8 words, we can have 8 bytes. So what this means is our index 8 is going to have 3 bits to correlate the address. So the size of the memory here is 32. That means I have 32 elements in the next level of cache, of which I can have 8 at any given moment. So what happens is, let's say my value is 00001, right? And so I want that, I check it for it, it's there, we're good. But let's say what I really wanted was 11001. So I go there, I check, let me erase this one. So I go to memory, I check to see what's in this particular block. Is it 00001? It is not. I want 11011. So here's what happens. I'm going to take this value here, and I'm going to go back and say, you need to go home, right? Swap it out. And then what I do is I go to 1101001, which is this one here, right? And I swap it in because that was the one that was requested. So these 3 least significant bits, you see 00, let me change color here, 001 here, 001, and 001. All those indexes correlate to the index in the lower level of cache where it's going to be. And the tag is which one of the specific possibilities it can be. So in this case, there are 4 possibilities. And that's why we have 2 here. I need 2 bits to indicate the 4 possibilities, and I need 3 bits to indicate how many items are in that lower level of cache. So in this case, the 4 possibilities are 00, 01, 10, and 11, and that possibility is for each one of those. And so that is where we take advantage of, so spatial locality is trying to get as many of those elements in the same ones as possible, and temporal locality is trying to have the ones here that are used the most. So when we go back to that previous problem, what we're saying is 95% of the time we're going to find the correct element here. But if it's not there, then 5% of the time I need to put it back and then go get the other element.
So I guess earlier than that, those few diagrams, earlier in this section 6, you concatenated the 2, the size of your tag to the size of your index.
And how many bits do I need to represent memory here? 5. And so how many do I need to represent here? 3. And so what's the difference? So what was the? So if I need 3 here and I need 5 here, your tag is 2, right? So tag is the number of possibilities that you have. So basically, it's just this number, the number I need here times the number of this number. So what I have 4 possibilities for each one here. So the tag indicates which one I'm actually using. Did I answer that question? All right. So this is direct associativity. So this is what's happening in cache memory. So we're going to put this together, with registers, we're going to put this together with your ALU, your control signals, and everything in next section. It's going to create a data path. Okay, so here's a problem where we're actually going to calculate out what you need. So here, we're given a memory of 16 kilobytes, where a block is 1 byte, so byte addressing, right? And a cache with 256 bytes. Determine the length of the index and the tag of a directly mapped cache. So now we're going to go through a slightly larger example. So we're kind of done this, but now we're going to do this example here where it's more complicated. So 16 kilobytes. So even though I've written it here, let me... What is 16 kilobytes actually?
16 times 10, or 1,024.
Mm-hmm. And so what is 1,024 in terms of 2 to the x power? Yeah, it's 10, right?
Yeah.
And so that means that 16 is 2 to the 4. So that's where, I'm going to make this a lot smaller now. So that's where we get 2 to the 14 from. So it's 16 kilobytes is 16 times 124. This is why I said you should know up through 2 to the 10. So this is 2 to the 10, and you know 16 is 2 to the 4. So 2 to the 4 times 2 to the 10 becomes 2 to the 14. So that's our memory size. So getting back to what you were just saying earlier, Joseph, the numbers that you should add up are 6 plus 8. And so the block is 1 byte. So it's just 8 bits. And then the size of the cache is 256 bytes. So that's block is going to be log 2 of 256, which is 2 to the 8. So therefore, our index, which is the least significant bits, is 8. And then we can use this equation here, 2 to the 14 divided by 2 to the 8 to get 14 minus 8, which is 6. Other things I've seen people doing, which is full credit, they see this, they get this number, and they go, okay, well, I know that 14 minus 8 is 6. So now this is the last part, and here's what this means. So I have a block is 1 byte, right? So each element of that memory is going to contain 8 bits. That's 1 byte. Let me scroll up just a little bit past the question so everybody can see the solution here, right? So we have calculated that our tag is 6. So we have 2 to the 6, which is 64. So that's 64 possibilities for each block in that lower level, right? And so that index contains 8 256 blocks in that level. And then, so now this allows us to store 16 kilobytes in a cache of 256 bytes. For the 256 bytes lower level of cache is much faster, and therefore we can actually use that swapping to take advantage of locality. And then, in the problem, we state that each block is a byte. So in data memory, when you're getting your items, you're seeing load word calculates index, and your memory is there. So basically, your load word is calculating which specific number you need here, and you get the next 3 to get your whole word. And so the reason why we use byte addressing is to be able to, reduce those block sizes to try to improve hit rate. So, does that make sense? Is now the whole point of load word and store word and doing times 4, or at least it's starting to make sense? Okay. All right. So does anybody have any questions on this before we move on? Yes, Joseph.
And so I guess if a block goes 1 bit, you just multiply their.
You would never have a 1-bit block. That's
Okay.
that's 0 and 1.
Just if you have something other than 1, you just multiply it by your.
Oh no, this is 1 byte. Okay, so 1 byte is 8 bits, correct?
Yeah.
So what if I made this 32? If I made this problem 32 bits, or the proper, let's say I said word, which is 32 bits. How would my answer change?
Your multiplier cache by your.
No, you're overthinking this. If where a block is 1 byte, and the cache is 256 bytes. So this would be, in my problem, I would change this to 256 words. This is actually a good question. So if each block is a word, so it's 32 bits, that's each memory element is 32 bits, right? So how would this answer change? That's it. So the cache size corresponds to tag and index. But each element in that memory, like if we go back up here, you see how we have some sort of block here? When I say block, that's just this. So you have some sort of value here that indicates, in that case, it would have been 32 bits, or it could have been 8 bits, or for the case of byte addressing. So I have some larger memory that I can't represent. So I move it to here, but at that point the block is the small amount of memory. Any other questions? All right, so this is the type of problem that you would encounter. I don't expect you to replicate every table. Typically what people will do is they'll work through it and then show the steps. See how I have the steps written down here? So they'll write the steps and then they will indicate this last table. So right now just learn how the steps work, and then I'm not requiring you to do everything. I've just gone in more detail than I expect on an exam. So given direct map cache with 8 words, there. So, and then the address references 22, 26, 22, 26, 16, 3, 16, and 18. Show the sequence for accessing the cache. Assume the cache is initialized as empty. So what I mean by initialized as empty is all of the valid bits are going to be 0. And by the way, it's going to end at 6.6. And the previous TGO we did was what? 16. Okay, so that'll allow me to have the homework assignment written up for next class. All right, so we'll just focus on this problem, then we'll be done. So this is 6.6, and the first thing I'm going to do is I'm expect you to convert all those numbers to binary. And so 22 is 10110, 26 is 11010, 16 is 10000, 3 is 00011, and 18 is 10010. So what you're going to notice is, since I have 8 words, you put it in your equation, and you're going to find out is that log 2 of 8 is 3. So your index is going to correspond to these least significant bits. So 0, 1, 1. So what you're going to notice is, so on an exam, if you convert them out and none of them are the same, then you've done something wrong. And the reason why is I want you to be able to see how to swap things in and out. So if you start seeing 2 of these are the same, or 3 of these have the least significant bits the same, then you're on the right path. So we start out, we're empty, just like we talked about. So everything is no. So the first access here is 22. So what we're going to do, we go to 1, 0. We go here and we put in we change this to yes, and then the tag is 1, 0 because it's the most significant bits. And all you have to do is write M of 1, 0, 1, 1, 1. So I've just put memory, but M of this value. So that's your way of doing that without having to write out a whole word, which is 32 bits, right? So that's step 1. So step 2 is 26, which we look at as 11010. So if we were to do that, we would say yes. We change the tag to 11, and this becomes M of 11010. So then the next step is 22 again. That's a hit. We're there. 26 is a hit again. So we have a hit. Very good. And then 16 is 10000. So we're going to go to 00. We're going to put the tag as 10. Change the valid bit to yes. And then we would put the word that corresponds to that particular element, right? So then, next step, we go to 3. 3 is 00011. We go to here. And then it's yes. And that's just, we put 00, and we do memory here. And then we go to 16 again. 16 is there, so it's a hit. And 18 is 10. So we go here, and this is where it's going to change. So we go to 00 here, 010, because that's our index. Uh-oh, that's not the number we want. So now we perform a swap. So go here, we get rid of that, we get rid of that. We swap it out. And then what we would do is we put it in here, and then we say change the valid bit to yes, and then it's going to be 18, so it's going to be 10. So that is your solution. And so when it's empty, that's a cache miss. So if you're doing millions of instructions, over time, you're going to get those very high cache hit rates. So if we scroll through here, go step by step, and we see the same thing again. We swapped it out. We had a cache miss. We had a cache miss. We had a hit. We had another hit. We had a miss, so we put in 16. And then step 7, 8, and 9 to solve it up. 3 was a miss, so we put it in there. 16 was a hit, so we left it alone. And then 18 was a cache miss, so we swapped out 16 for 18, and I indicated here tag 11, 010, index out for tag 10, 010, index. So that's the whole idea behind this cache hierarchy. Taking advantage of these blocks, which are faster but more expensive, to improve computing performance. So remember all the way back in section 1 when we talked about Amdahl solve, where let's talk about how we improve the ALU. Here we are improving memory to try to improve computing performance. So in next lecture, we're going to be going over set associativity. We're going to finish up section 6. Does anybody have any questions before I dismiss you? So make sure you understand all the stuff with muxes and all the stuff with converting C to MIPS. And then I will post your homework, but it is TGOs 6.6 through 6.16, and then example questions 6.1 through 6.6.